As the last lecture in this module, and as the module being the last in this whole session, we will look at not only the applications of PSR and SPSC concepts beyond what we have discussed earlier, but also look at wrapping up this particular session on the benefits of PSR and SPSC concepts for P risk assessment. Now, first we will look at the relationship of PSR and SPSC to equilibrium P concentrations. In Module 4, Lecture 3, we looked into the relationship of the P saturation ratio and isotherm parameters such as the equilibrium P concentrations and the strength of P bonding. What we noted is the Langmuir-KL approaches 0 and EPC 0 increases after the change point, that is, after the threshold PSR, which we know is defined as 0.1. This particular relationship is also applicable to the Freundlich KF. Now, let us look at the relationship between SPSC and EPC0 for upland soils. What we have here, the BH of aliquot profiles from 3 sites, S1, S2, and S3, and the BT of pale dirt profiles from 3 sites again, S4, S5, and S6. 6 to 8 profiles were sampled from each site depending on the land use characteristics, so that we have a total of 56 BT and 67 BH samples. Methods: SPSC was computed for all BH and BT horizons, and EPC0 was determined for all BH and BT horizon soils. Just as a matter of reminder, SPSC can be computed from P, iron, and aluminum in an oxalate, Mehlich 1, or Mehlich 3 solution with the appropriate conversion factors. And EPC is determined as explained in Module 4, Lecture 3. So, when SPSC is positive, EPC0 for the BH and BT horizons is minimal. This is very similar to the relationship of SPSC and water-soluble P. You can see a figure on the left, and the open and closed markers simply represent positive and negative SPSC, and we're talking now of BH and BT horizons of aliquots and pale dirts. The reason, as you know by now, is that the surface horizons, especially of spodosols, do not have any P retention capacity, and therefore it is less likely to provide a good relationships between SPSC and EPC0. Now, what we find is when SPSC is negative, water-soluble P increases linearly, but the relationship of negative SPSC with EPC needs further evaluation, particularly for wetland soils with high organic matter content. 40 surface samples, 0 to 10, were collected from the edge and center of wetlands of 8 beef ranches in the Lake Okeechobee watershed to evaluate the relationship of SPSC and EPC0. Mehlich 1 P, iron, aluminum were analyzed for all soils and SPSC calculated. EPC for each soil was determined. Here is the relationship of EPC to SPSC. SPSC is on the y-axis and EPC on the x-axis. What we note is that EPC is a minimum when the soil is a P sink, and it's irrespective of the organic matter content of the soil. The EPC increases once the SPSC becomes negative. but the EPC is likely related to the organic matter when SPSC becomes a P source. This is the area that needs additional work. Now, can we obtain KL from SPSC? We noted earlier that at the change point, that means when SPSC is 0 and then it becomes negative, the Langmuir KL is basically 0. There is no P retention, P is not held. But when it is positive, and we looked at PSR and KL, we noticed that there are several points that are all in the positive section, but there is no real relationship, simply because the PSR does not take into account the additional iron and aluminum that's present in the soil, and that is taken care of for SPSC. Now, what we notice is when SPSC is positive and the KL is related to SPSC, we find that we have a linear relationship. And therefore, if we know the SPSC of a soil, we should be able to obtain the KL value of the soil. Now, it is somewhat similar for obtaining KF from SPSC, but the slight difference is when you're looking at KF below the change point, then you can obtain a linear relationship, that is when SPSC is positive. But when SPSC is negative, that is above the change point, rather than showing the KL value that's suggested, there is no P retention, the KF value actually is linearly related as shown in this diagram. And therefore, KF can be obtained for both positive and negative SPSC values. Now, an overview of the PSR and SPSC concepts. Let us start with the threshold PSR of 0.1, or when SPSC equals 0, the soil is neither a P source nor a P sink, and this is the block that you note in the center of the slide. To the left, you have the PSR, where it is less than 0.1. So SPSC is greater than 0, that is SPSC is positive, and the soil is a P sink. Now, under those circumstances, water-soluble P and EPC0 will resist increasing. Iron and aluminum concentrations are primarily responsible for P retention, and therefore there is no P release. At the threshold when you know that the soil is neither a P source nor P sink, but when you reach the PSR greater than 0.1 or the SPSC is less than 0, you know the soil is a P source. This is shown in the third block in this particular diagram. Now, water-soluble P or any other measure of releasable P, including the EPC, will begin to increase. P release will depend on several factors: iron and aluminum, for example, the solubility of the P source, and perhaps organic matter. We need to work more on understanding the concept of organic matter as it relates to SPSC when SPSC is negative. Now, how do we use the PSR and SPSC in risk assessment of soils? What would be the suggestion? Well, we have a soil sample. Determine the P iron aluminum in a soil test solution, example Mehlich 1 or Mehlich 3. Calculate the PSR and SPSC for the surface soil, 0 to 10 centimeter depth, or maybe 0 to 15 centimeter depth if it's for agronomic purposes. And when the PSR is less than 0.1 and the SPSC is greater than 0, the soil is a P sink. The soil does not pose an environmental P risk. But when the threshold PSR is 0.1 and the SPSC is 0, and you have a soil which neither a P source nor a sink, the recommendation is to determine SPSC for additional soils in the location. And if you notice no problems, determine the SPSC at intervals, say once a year, to confirm that the soil continues to remain a P sink. We'll suggest a one-time deep soil sampling to verify that P has not moved vertically. You will realize that if you have a soil such as spodosols, you may not get much P in the surface, but it may have moved down to the spodic horizon. Now, when the PSR is greater than 0.1 and SPSC is less than 0, your soil is a P source. So additional soil samples need to be collected, depth of soil to a minimum of 1 meter, or to the spodic or argillic horizon if present, recommended to evaluate P risk due to leaching. Now, in summary, the lecture illustrates the power of the PSR and the SPSC concepts in understanding P storage and release from a soil. The simple manner in which PSR and SPSC values can be added or can be computed from P iron aluminum in a soil test solution adds significantly to its usefulness. EPC values obtained by construction of isotherms we know is a time-consuming process, so it's so much easier to obtain the values from just soil test data. You'll notice that the relationship of EPC naught to SPSC confirm that EPC values are minimal below the threshold PSR, and we also know that Langmuir KL and Freundlich KL can be obtained from a Langmuir KL SPSC or a Freundlich KF SPSC relationship. Here are a few references that are directly related to this particular topic.